For my advanced data science final project, I did an analysis of transportation times around cities to produce a city recommender. So the general overview of this project. So I am going to move somewhere in the next year, and a lot of my peers are doing that too. So one way I was thinking about to evaluate cities is based on the transit options that are available. So I would like to compare driving versus biking time around cities in various routes. So the way I did this was I generated different routes, common routes around a ton of different cities. There's 100 cities, and those are plotted on the Google Maps in this bottom corner here, minus Fairbanks, Alaska. It wouldn't fit in the screenshot. And so the first stage of the data science analysis was to cluster these different cities to find similar cities, and then I could simulate transactions from those clusters. And from those transactions, just smaller groups of cities that are similar in some way, I could do market basket analysis and produce recommendation association rules and recommendations based on an input list of cities. That's the overall goal. So my data collection methodology is a little convoluted, so stick with me here. The end goal is to compare driving versus biking times for just common routes navigating around cities in many different cities. So first I came up with 100 different cities all over the country. This started out as like, oh, I might want to move here, and ended up as I've heard of this city before. So you get someplace like Forks, Washington. And then I came up with a list of common places that a resident might want to go, right? So might want to go from home to downtown, or from downtown to some event space or stadium. So then I got common routes between those places because of the way my Google Maps API works, which I'll get to. I couldn't just compare every I couldn't compute the route from every place to every other place within a city. So I had to find common routes. Like, for example, I don't really care how long it takes to get from the grocery store to the hospital. If that happens, I'm probably going to be in an ambulance. I've never made that trip, I don't think, in my life. Um, so I just came up with a list of common routes for each city. So this ended up being a list of origins and a list of destinations where I could go. I wanted to know how far it took to get from every origin to every other destination. So I ended up with the origins being home, the grocery store, an event space or stadium, a hospital, and some sort of like local iconic spot, which, if your friend is coming to town for a weekend, that might be where you take them in any given town. So for Boulder, that was Chautauqua. Oh, and then I can, yeah, explain those pictures in a second. The destinations were home, a nearby city, downtown, and some sort of park or nature spot. So that would be 800 latitude longitude points, which I did not have time to find. So I had Claude take this description of these points and the list of cities and had it generate points for every city. And I went through and did spot checks. It seemed actually quite good. So these are some of the places it picked for Boulder. And for home, I had it approximate it with some sort of neighborhood near town. So for Boulder, it was somewhere in North Boulder, sort of north central, um, by Iris Avenue, I think. And the so for downtown it was Pearl Street, and then that's the hospital, and for the stadium it chose Folsom Field. So the exact location of those points I'm not super concerned with, because again the main idea is to try to evaluate driving times versus biking times, just getting around a city. So as long as the points are sort of spread around a city, that's all I care about. So to get the routes between those points, I use the Google Maps Distance Matrix API, which basically you give it a list of origins and a list of destinations, and it calculates it gives you route information for all of those. So distance and time, all I really cared about was the time. Uh, and I had $300 in free developer credits for making a developer account, which limited how many routes I could evaluate basically. So that's why I only chose the 20 or 19 routes that I did. So once I have that data, there's different ways to represent it, right? Primarily, I want to compare drive versus bike time. So for each city, the distance matrix API spat out two different matrices, one for the time it takes to bike the routes in a city and one for the time it takes to drive the routes in a city. So there's different ways to compare those. The most straightforward, which is the one I tried first, is the time to bike minus the time to drive. It's pretty intuitive. It's negative if it's faster to bike. It's positive if it's faster to drive. Uh, just a very straightforward comparison. Another pretty straightforward one is the ratio of drive time to bike time. And another one I tried was the difference in bike and drive times divided by the drive time, which I tried because I wanted to sort of get the difference in time as a percentage of the drive time, but it ended up not being very well behaved than the more straightforward ratio when it came time to cluster. And another representation I used was the unlabeled differences. So the idea here is that the points are pretty arbitrary. The points within a city are pretty arbitrary anyway. So I don't care about the exact layout of a city, right? I don't care specifically if the grocery store is super far away, but the nearest park is next door. I don't, I don't really care about the specific layout. So I removed all of the labels and sorted each city, each point, by its 20 or 19 routes, um, by how long each of those routes, the difference in drive time and bike time for each route. So that way I can just compare the smallest difference bike to drive to all of the other smallest difference in all of the other cities to the essentially the closest thing in all of the cities, and the largest difference, so the largest gap. So usually this is like downtown to nearby city, or yeah, like home to the nearby city or something, but sometimes the nearby city is really close and the nearest park is super far away. So that compares travel times a little more directly. So it's hard to look at this 20-dimensional data, 19-dimensional data, directly. So this is the type of plot, one of the type of plots I was looking at to examine the spread and the scale of the data when I was trying to evaluate a new representation. So it's just every fifth city plotted with all of the points for that city on the same scale. So this is the one for just the ratio. So once we had all those points, let me just move myself here. Once we had all those points, then we could cluster. So I wanted to cluster each of those 100 points, each of those 100 cities, and figure out which ones are similar to each other. And it's hard to look at the 20-dimensional data and get an idea of what this should be. So I'm very reliant on the elbow method to try to find the correct number of clusters to model this data. So this involved plotting the inertia, which is the within cluster sum of squares. It's sort of a measure of how accurate the clustering model is versus the number of clusters. So I want the minimum number of clusters. I want to get the number of clusters at the point of diminishing returns, where more clusters would not really lead to a much more accurate model. It would just lead to overfitting essentially. So for example, in this top corner here, you can see for the unlabeled differences representation of the data, the correct number of clusters seems to be either 5 or 7. And then looking at the actual clusters themselves, it turned out 7 is a better number of clusters for this representation. So I found the cluster models and the clusters of cities for all 3 data representations. The goal is to find just clusters of similar cities off of which I can build transactions later. And I also used the sklearn library for the Gaussian mixture model clustering. So this had a few more parameters I needed to tune. So I was spent a lot of time looking at graphs like the one in the bottom corner there, looking at the BIC measurement, um, which, so that allowed me, first I had to tune the um, reg covariance variable parameter so that the cluster covariance matrices, so basically the matrices that outline that indicate the shape of the cluster, wouldn't collapse into some uh, singular matrix and essentially capture no data and provide nothing. Another thing I had to do was figure out, I had to run multiple um, initial guesses so that it would be less prone to finding local minima and more prone to finding a global minima. Um, and once I had those two things, then I had a reasonable looking BIC versus number of components, BIC being the sort of the measurement of how accurate a Gaussian mixture model is, with penalties the uh, for having too many components, so for overfitting. So that, for this particular example, in the raw difference data, the number, not raw, for the difference time bike versus time drive data, the correct number of components or clusters, there were 14 clusters. So I ended up with 6 groups of clusters, 3 for each method. One other thing I would like to do that I didn't have time to get to, that would be a good bit of further research, would be to run these clusters on the principal components of these data, because 20-dimensional data clustering is, I think, unwieldy, and I'm sure there's a lot of essentially noise in those 20 dimensions. So doing a principal component analysis and then redoing the clustering, I think, would be very insightful. And let's move myself again. So now that I have the clusters, I want to simulate some transactions. So the goal is to recommend cities using market basket analysis, where each market basket is a group of cities. I had to keep reminding myself of that. Kept forgetting that. And I need transactions to do this. So transactions, in theory, are groups of similar items, or groups of items that need to be grouped together. And clusters are groups of similar items. So if I take combinations within those clusters, they should be very similar to one another. So they should provide a decent sort of approximation of city preferences. I generated every combination of size 5 of within every cluster from the previous step, all 48 clusters. And this turned into about 6 million transactions. I think another area of further research would be to randomly sample the transactions or randomly sample the clusters to get transactions, because you'd have a lot more control over the size of the clusters, how many there were, and just all sorts of things about the cluster or the transaction generation process to make it probably more accurate. But I ended up doing combinations of the transactions. So some of those are seen in this bottom corner here. It's like 5.87 million ended up with, which was probably too many, as we'll see later. But a lot of them were very similar. So this is kind of what I was looking for, is like, okay, Albany and Albuquerque are going to occur in a lot of different transactions. So potentially there's an association between those two, because they appeared in a lot of clusters together. So they will appear in a lot of transactions together. So once I had those transactions, then I could generate frequent item sets. And I use the a priori algorithm to do this. With close to 6 million transactions, this was pretty unwieldy. So I had to do a couple things differently from what we learned in class. First, I separated the first iteration of generating the one item sets, because calculating compute support with all the set math would have taken forever for all 6 million of those. So that was separated in its own step, and you could just count the number of transactions each item set appeared in and compare that, and that was easier. Then, or quicker, I guess. Then after that, it just goes to the regular join prune steps for a priori, and it finds all item sets which are frequent with a minimum support. I found that 0.1% of transactions worked. And then that gave us about 1,500 frequent item sets. And then from these, we could generate and test all possible association rules. And the association rules would be of the form sort of a number of antecedents, which co-occur frequently with a single consequent city. Um, so typically you'd evaluate these with lift, which sort of measures if that association happens more than random chance. That didn't really work here because the number of cities is significantly smaller, it's 100, than the number of transactions, several million. So that means that most cities are in maybe not a majority of the transactions, but many, many, many transactions. Uh, so the lift was essentially always saying this is due to random chance. This association is due to random chance. So I was purely filtering the association rules on confidence. This is an example in the bottom corner here of some of the association rules generated. I had a couple hundred. And here's kind of a gaffe that this took me a while to figure out. Within the compute support function, this is similar to the one I wrote in class for like 15 transactions. That doesn't really work when you have like 6 million transactions to loop through every transaction for every candidate. I did that. It runs a lot faster if you don't loop through 6 million things within another loop. So from these association rules, then I was able to produce a city recommender. Yeah, a city recommender. So basically, you give it a set of cities, maybe a set of cities that you would like, and it'll recommend similar cities. So it'll look up all of the possible antecedents, so all subsets of your input set, and it'll count the number of times that each city is recommended by any subset of your input list. So, and then it'll display the most highly recommended cities. So I think it actually works okay. This is one example. These are cities I've been to and I enjoy. And the recommendations: Corvallis, Oregon, I've been there, I enjoy it. Salt Lake City, I've been there, I like it. I've never been to Tacoma or Hayward, California, or any of the other cities, but maybe I should go to Tacoma or Hayward. Yeah, so that is essentially the product that I've produced, and these are the references I used to do it. Thank you.